Discover the counterintuitive phenomena that occur when fluids flow at microscopic scales. At microscopic scales, fluids behave in ways that completely contradict our everyday experience with liquids. The Reynolds number reveals the first major paradox in microfluidics. The Reynolds number equals density times velocity times length, divided by viscosity. At microscale, Reynolds numbers are tiny, so flow is always laminar with parallel streamlines that never mix. The paradox is that mixing becomes nearly impossible because there's no turbulence to stir fluids together. The second paradox involves how diffusion takes over at small scales. Red and green fluids don't mix by flow, but molecules randomly diffuse across the boundary over time. Diffusion time is proportional to length squared, so smaller distances mean much faster mixing. Surface tension becomes dominant at microscale, creating unexpected effects. Surface tension forces pointing outward become more important than gravity at microscale. The paradox is that droplets can actually climb walls against gravity due to capillary action. Pressure drop behaves counterintuitively at microscale. Narrowing a channel creates massive pressure drops because viscous forces dominate at small scales. Pressure drop is inversely proportional to height cubed, so tiny changes in size cause huge pressure changes. These paradoxes show why our intuition fails at microscale. Viscosity beats inertia, diffusion beats convection, surface beats volume, and pressure dominates at microscale. Understanding these paradoxes is essential for designing effective microfluidic devices for medicine and science.